Hello everyone, this is our first session on straight lines, that is pairs of straight. That's what we're starting with today. Okay, so basically we are aware of equations of lines, straight lines. We're going to do combined equations of two lines. Okay, so let us begin with the chapter. I am directly sharing the chapter textbook PDF right now with you because there are theorems in the beginning and then we can go on to the numericals. Okay, comparatively it's a very simple chapter to understand because we are used to equations of lines, linear equation of lines, if you remember. So how were we representing those lines? So we had equation as ax plus by plus c, remember, so equal to 0, where a, b, c are constants, not 0 simultaneously, representing a line in the xy plane. We've done the forms like y is equal to mx plus c. We've done forms like x2 minus x1 is equal to y2 minus y1 is equal to m into x2 minus x1. So that is also an equation of a line, right? When you don't have the c part of it, that is y is equal to mx, then those lines pass through the origin. So we have done equations of lines. Now we are going to do combined equations of these lines. Now let's study two lines simultaneously. This we need the concept of the combined equation of the line. So now what do we understand by combined equation? Let us observe. Okay, an equation which represents two lines is called as combined equation of these two lines. Let u equal to a1x plus b1y plus c1 and v equal to a2x plus b2y plus c2 be the equations of two lines. Okay, u equal to 0 and v equal to 0. So we're representing two lines over here by u and v. Okay, one will use the marker. Yes, so here we are, two lines, u equal to a1x b1y plus c1 and v equal to a2x plus b2y plus c2, both equated to 0 to represent lines. We know that equation u plus kv is equal to 0. Okay, now this is adding of the two equations, represents a family of lines. We have done this previously. The general equation of lines together, it's called as u plus kv equal to 0. Okay, represents a family of lines. Let us interpret the equation uv equal to 0. Now what is uv equal to 0? So the first theorem says that the equation uv equal to 0 represents the combined equation of lines u equal to 0 and v equal to 0. Basically, giving an equation for both the lines together. Okay, so if they are coinciding, then we need a single equation representing them. How do you get that single equation? Okay, so we have, considering the lines u equal to 0 and v equal to 0 as a1x plus b1y plus c1 equal to 0 and a2x plus b2y plus c2 equal to 0. Now we say that let p x1 y1, if in the figure you can see p x1 y1, be a point on the line u equal to 0. Now if it is a point on that line, then it satisfies the equation of that line. So the equation will change to, we'll put it in the equation, it will become a1 x1 plus b1 y1 plus c1 equal to 0. Now what do we have to prove? We have to prove that x1 y1 satisfies the equation uv equal to 0. So now I have a multiplied equation of the two lines u and v. Okay, we have to prove that this x1 y1 which lies on u equal to 0 also lies on the combined equation uv equal to 0. So how do you get that? So we prove LHS equal to RHS. Okay, so what is LHS? U into v. A1 x1 plus b1 y1 plus c1 into a2 x1 plus b2 y1 plus c2. Okay, so when you substitute the point x1 y1, we know that u equal to 0, that is a1 x1 plus b1 y1 plus c1 is equal to 0. So we substitute that as 0 and so we get the right side as 0. Therefore, x1 y1 satisfies the equation uv equal to 0. This proves that every point on the line u equal to 0 lies on uv equal to 0. So the equation, the combined equation says that if I have an equation u into v equal to 0, and if one point is lying on u equal to 0, then it will lie also on uv equal to 0. Similarly, we will prove that if any point is lying on v equal to 0, then it also satisfies uv equal to 0. Same method. Now, the reverse way, that is, if any point is lying on this combined equation, then it is either lying on u or on v. So, you have to prove that. So, we say now let r x dash y dash be any point which satisfies the equation uv equal to 0. Okay, so we substituted in that equation a1 x dash plus b1 y dash plus c1 into a2 x dash plus b2 y dash plus c2 equal to 0. Okay. Now, in this proof, there is one mistake. Okay, if you can observe what they have done over here, a1 x1 plus b1 y1 plus c1. Now, x1 y1 was lying on u equal to 0. What they've also done is they have substituted it in the second equation, that is a2 x1 plus b2 y1 plus c2. Okay, so what should have been substituted? It should be x2 y2 over here. A2 x2 plus B2 y2 plus C2, where x2 y2 lies on V equal to 0. Okay, and now the next step would be, but the first equation is equal to 0, and therefore the combined equation is 0. Same way you do it for V equal to 0. Okay, now let us see about x dash y dash. Now, x dash y dash, a1 x dash plus b1 y dash plus c1 into a2 x dash plus b2 y dash plus c2 is equal to 0. Okay, so now they've put x dash y dash in the combined equation of uv, and they want to prove that u is equal to 0 or v is equal to 0. So normally we write this as, therefore either left side first bracket is 0 or the second bracket is 0. That is a1 x dash plus b1 y dash plus c1 is 0, or a2 x dash plus b2 y dash plus c2 is equal to 0. Therefore r x dash y dash lies on the line u equal to 0 or v equal to 0. Okay, so it's basically just proving that if one point lies on u equal to 0, then it lies on uv equal to 0. If one point lies on v equal to 0, then it also lies on uv equal to 0, and then vice versa. Okay, so every point which satisfies the equation uv equal to 0 lies on the line u equal to 0 or the line v equal to 0. Therefore, equation uv equal to 0 represents the combined equation of lines u and v. Okay, the combined equation of a pair of lines is also called as a joint equation of a pair of lines. Equation u equal to 0 and v equal to 0 are called separate equations of lines represented by uv equal to 0. Okay, now the next theorem or the next topic, homogeneous equation of degree 2. Now, what do we understand by the word homogeneous equation of degree 2? All the terms in that equation should have the degree 2. Okay, now they've given an example over here to show what is homogeneous and what is not. So if you can observe this equation here, x square plus 3xy minus 2y square plus 5x plus 2. Let us find out the degree of each term. So first term is 2, second term is 2, third term is 2, fourth the degree is 1, and last the degree of constant term 2 is 0. Okay, so degree of 0 is not defined. Okay, so now if you can observe, every term does not have the same degree. Okay, so that is just basically trying to understand what is degree. Now what should be homogeneous then? Each term should have the same degree. An equation in which the degree of every term is same is called as homogeneous equation. Okay, so they've given an example for that. X square plus 3xy is 0. So what does that mean? First term degree 2, second term degree 2, and 0 has no defined degree. So therefore, the degree of this equation is 2. Okay, so if you can observe, all these equations over here are homogeneous equations because they have the same degree. Okay, homogeneous equations of degree 2 in x and y has the form. Okay, now this is the general form of an equation of degree 2 in x and y. Okay, this is not equation of a line. We are going to prove that equation now, but any homogeneous equation of degree 2 is given in the form ax square plus 2hxy plus by square. Okay, Now the next theorem, the combined equation of a pair of lines passing through the origin is a homogeneous equation of degree 2 in x and y. Okay, now an important part. Combined equation of a pair of lines, remember uv equal to 0, a1x1, or rather a1x plus b2y plus c equal to 0, and a2x plus b2y is equal to 0, b2y plus c2 equal to 0. Those are the two equations of single lines. Combined equations, we multiply these equations. Now they say that combined equations of a pair of line passing through the origin is a homogeneous equation of degree 2 in x and y. So there are two conditions in this theorem. First, the combined equation of the lines, and secondly, those lines have to pass through the origin. Okay, so when lines pass through the origin, the c constant part of it is missing. Okay, it's not there in the equation. What does the equation look like then? So let a1x plus b1y equal to 0 and a2x plus b2y equal to 0. You can observe the equations here. Okay, they're passing through the origin, and therefore they don't have the term plus c1 and plus c2 in them. Okay, so they're passing through the origin. These are the two equations passing through the origin. What will be their combined equation? Basically, we have to multiply them. Okay, so if you can observe here, they've multiplied the two brackets, and when you multiply the two brackets, you get a1 a2 x square plus a1 b2 plus a2 b1 xy plus b1 b2 and y square equal to 0. Now what I will tell you is, let's not look at the constant part of it. Okay, so what we'll do is we'll hide the constant part of it. So we'll, one second. Yeah, so we'll not look at the constant. We'll not look at this constant also, and we'll not look at this constant. What you can see after multiplying the two equations, what is the degree of the first term? It is 2. Second term 2, and third term 2. So what does this theorem say? The combined equation of a pair of lines passing through the origin is a homogeneous equation of degree 2 in x and y. Is that true? Degree 2, yes. Is it in x and y? Yes. That's what we had to prove in the theorem. So now let us remove those marks. Okay. Now what are all these terms that we had colored? They are the constants. So instead of a1, a2, we put a. Instead of a1 b2 plus a2 b1, we are putting 2h, and instead of b1 b2, we are putting b. So this equation simplifies to ax2 plus 2h xy plus by2 equal to 0, which is a homogeneous equation of degree 2 in x and y. Okay, so comparatively a simpler proof. Okay, now the questions of in this type, if you know, would be verify that the combined equation is a homogeneous equation. So basically you have to multiply them and get the homogeneous equation. Okay, so if you get degree 2 in each of the terms, then it is a homogeneous equation. Okay, now very important part over here. Okay, this, the combined equation, one second, yes, so let me highlight this for you. Okay, so it says that yeah, the combined, sorry, one second. The combined equation of a pair of lines passing through the origin is a homogeneous equation. Correct? We just proved this of degree 2. But every homogeneous equation of degree 2 need not represent a pair of lines. Very important. Okay? They've given an example for the same. X square plus y square equal to 0 is a homogeneous equation, right? Both are in x and y. Degree is 2, but it does not represent a pair of lines. Okay, so important theorem says that combined equation of a pair of lines passing through the origin is a homogeneous equation of degree 2, but every homogeneous equation of degree 2 need not represent a pair of lines. Okay, let's move on to theorem 3 now. Okay, so what is theorem 3? Homogeneous equation of degree 2 in x and y is given by what? Ax square plus 2hxy plus by square equal to 0. Now it says that this homogeneous equation represents a pair of lines passing through the origin if, okay, now the reverse part of it. Okay, what we were saying, any pair of lines or the combined equation of a pair of lines passing through the origin is a homogeneous equation of degree 2 in x and y. The third theorem says that homogeneous equation of degree 2 in x and y, ax square plus 2hxy plus by square equal to 0, represents a pair of lines passing through the origin only if h square minus ab is greater than equal to 0. Okay, now the proof has two cases over here. Case 1, if b is equal to 0. Now, if b is 0, we get the equation as ax square plus 2hxy equal to 0. So, we get this as simplified two factors x and ax plus 2hy equal to 0, which is a combined equation of two lines. Which are those two lines? X equal to 0 and ax plus 2hy equal to 0. X equal to 0 is the equation of the y-axis. So it of course passes through the origin, and ax plus 2hy does not have a constant term, hence that also passes through the origin. Clear? So when b is equal to 0, yes, both the lines passing through the origin, so combined equation is also passing through the origin. Case 2, if b not equal to 0, then what do we do? So then we use the equation abx square plus 2hbxy plus b square y square equal to 0. Where is this equation coming from? From here, ax square plus 2hxy plus by square. So what are we doing? We multiply equation 1 by b. What is this equation 1 that we are multiplying? Just let's check. So this is our equation 1, the combined equation of two lines. Okay, that is your equation 1. This I am going to multiply with this equation 1 is multiplied with b. So what do we get? abx square plus 2hbxy plus b square y square. Okay, let's go down. Yeah. So now what we can see is, sorry, over here. So you can observe that we have multiplied this equation here, abx square plus 2hbxy plus b square y square, right? So multiplying it, you get this. Then what do we do? Shifting abx square to the right hand side, we get minus abx square, and then on the left and right, we add h square x square to complete the squares. Okay, we get two factors after doing that. Now, what are these two factors? Let's come to the factors directly after solving. So you get these two factors, h plus, second, wait, h plus root of h square minus ab, sorry, h square minus ab, x plus by, into h minus root of h square minus ab x plus by equal to 0. So you can observe these are two equations of lines. So which is the combined equation of the lines h plus root of h square minus ab into x plus by equal to 0, and h minus root of h square minus ab into x plus by equal to 0. So it gives you equation of two lines. Okay, as b is not equal to 0, we can write these equations in the form y equal to m1x and y equal to m2x. So when you write these two equations in this form, which form are we talking about? When you write these two equations in y is equal to mx form, okay, y is equal to m1x and y equal to m2x. What are the m1 and m2? m1 and m2 are basically slopes of these two lines. What are they? Minus h1, sorry, minus h minus root of h square minus ab upon b, and minus h plus root of h square minus ab upon b. Now these two slopes m1 and m2 are very important. Okay, so we have to remember them while we're solving the sums. we're finding equations or slopes of lines from the combined equation, we can use this and get the equation directly. Okay, because see, y equal to mx is the general form. If you have the slope, then you can write the equation from the combined one. So if a combined equation is given to you, you require only the slope to find the separate equations of the lines. That's why these m1 and m2 are very important. Minus h minus root of h square minus ab and minus h plus root of h square minus ab upon b. Okay, so that is what we get from our derivation. Now, what are the remarks of these derivations? Okay, thus it says that equation abx square plus 2hbxy plus by square represents a pair of lines passing through the origin. One second. Passing through the origin if h square minus ab is greater than equal to 0. Okay, so what are the remarks of this derivation? H square minus ab is greater than 0, then lines represented by 1 are distinct, right? Because then you have two slopes, so you have two different lines. If h square minus ab is 0, then the lines are coincident. And if h square minus ab is less than 0, then the equation does not represent any pair of lines. If b is 0, we have observed we get two lines which pass through the origin. If h square minus ab is greater than equal to 0 and b is not equal to 0, then we get two lines with different slopes m1 and m2. Okay, now this part over here, this fifth one over here is very important again. Okay, this entire fifth point we have to remember while solving the sum. H square minus ab, slope m1 m2, m1 plus m2 and m1 into m2. We require them to get combined equations. Okay, also, yes. So what we can see here, slopes of the lines are m2. One second. Let me highlight the entire thing in a better way. Not like this. This is like scribbling. Just a minute. Okay. Okay. So we need to remember this. Sorry. Yeah. This. Then this over here. Slopes of the two lines. Then this, their addition, that is m1 plus m2. What is it? m1 plus m2 is minus 2h upon b. Multiplication m1 into m2 is a upon b, and the quadratic equation in m whose roots are m1 and m2 is given by. Very important, while solving the sums we require this. M square plus m1 plus m2 into m plus m2 is equal to 0. Okay. Now, m square as it is, it's a quadratic in m whose roots are m1 and m2. How do you write it? M square minus m1 plus m2 into m plus m2 equal to 0. And you substitute the value of m1 plus m2. And okay, here I think it should be m1 into m2, which is not written. Let me just put this. This textbooks makes so many mistakes. Just a minute. Black. Yes, over here we should have m1 into m2, okay, which is a upon b. So that is what is the equation in m. So they could tell you to find the equation in m if the slopes of the two lines are given to you. Okay, so we should be able to write that as well. Now this brings us to the end of explanation of the first three theorems. Okay. Now, if you can see here, they've written bm square plus 2hm plus a equal to 0. What does this equation represent? Let's go up and check. 1 minute. So they've taken LCM over here. So we get Vm square plus 2hm plus a equal to 0. Okay, this is not here. Yeah. Vm square plus 2hm plus a equal to 0. This equation 2 is called the auxiliary equation of equation 1. What is our equation 1? It is the representation of combined equation, okay, and roots of equation 2 are slopes of lines represented by equation 1. So I told you those two equations are very important. They give you the slope of the two lines separately, and from there you can directly make the equations of the line. Okay, so I think we're clear with the three theorems. For your exam point of view, the proof, I wouldn't say it's not important, of course it is, but the final product of the proof is more important for the sums. Okay, so whenever you're learning or whenever you are revising this chapter, go through the final equations so that you remember what is to be substituted when I have to find out the slopes, when I have to find out separate equations, when I have to find out the combined equations. Okay, in the next session, we begin with the first exercise of this chapter. Thank you so much.